Hey guys, today we are going to discuss the solutions for round C of Google Kickstart that happened yesterday. So let us discuss. Let us start with problem A. So in problem A, we require a seven character password which satisfies the following requirements: that it should have at least one number, at least one small letter, at least one capital letter, at least one special letter, and at least seven characters. So some of the constraints might already be satisfied in the existing password that the user has set, or otherwise we might need to add some letters to satisfy all of these conditions. So I define like four booleans, which is like num for number, down for small letter, cap up for capital letter, and spz for special letter. If any of these are satisfied, then we don't need to include them ourselves. Otherwise, we might need to include them ourselves. And later, we will just check the size of the string. If it is less than 7, we'll add some random letters just to get it to equal to 7. And that will be the smallest possible password. So let us look at how I have coded it. Yes. So I have defined these four boolean variables. Okay, it should be 0 here. So I check if it is a number, I say num is equal to true. We do it for every character. If it's a small letter, we say down is equal to true, up is equal to true, and spz is equal to true, as I mentioned earlier. Now, if any of these constraints are not satisfied, we add the number or small letter or capital letter or special character. And now, if the size is still less than 7, after adding all of these characters, we just need to add random characters just to make the size equal to 7. So while size is less than 7, we just add a random character A. And once this is done, we just print the string. So this is the solution for the problem. Now let us move to the second problem. Okay. Okay, problem B. Now we know that since either Allen or Barbera has to have each number from 1 to n, the total sum would be 1 to n, 1 to n for both of them, adding both of them together. That is n into n plus 1 by 2. Thus Allen's sum will be the xth fraction of the total sum. So Allen's sum will be n into n plus 1 by 2 multiplied by x divided by x plus y. So for this sum to even be a positive integer, since all of the possible numbers that Allen can take are positive integers, so sum can only be positive integer. So for this formula should also give a positive integral sum for Allen. So for that we need to check if n times n plus 1 times x should be divisible by 2 times x plus y. If it is not divisible, we can instantly say that it is not possible. Otherwise we can say that it is possible, and I will show it. So let's say we get a positive integer value which is less than n times n plus 1 by 2 for Ln. I can say that we can always have a subset such that this particular sum is satisfied. So this is because the maximum sum that is possible is n times n plus 1 by 2 if you take all numbers from 1 to n, and let's say we want a smaller number, then we have all possible decrements possible. So we can remove 1, we can remove 2, remove 3, we can remove n. Then after n we can remove n plus 1, which is by removing n and 1. We can remove n plus 2, n plus 3. So there is no particular subset which we can't remove from n into n plus 1 by 2. That is why for all of the numbers from 0 to n into n plus 1 by 2, it is satisfiable using a particular subset. Okay, so now how do we find such a subset? Let's discuss that. So let's say that we have n is equal to 5. So we have numbers from 1 to 5 and we require a number 10. So the solution I propose is that we go from a descending order, and if at a current point we have such an element which is lesser than the sum, then we just take it. So for example, we have 5 here, it is lesser than the required sum of 10. So we just grab this element. So after we take it, the new required sum would be 10 minus 5, that is equal to 5. And our current subset would be 5. Now we go to 4. Now is it lesser than or equal to required? Yes. So we take it as well. So now required would be equal to 1, and we have also grabbed the element 4. So now our subset is 4, 5. Now we look at 3, it is larger than 1, so we ignore it. We look at 2, it is larger than 1, we ignore it. And then we have 1, which is less than or equal to required, so we take it. So now our current required value will be 0, and our subset will be 1, 4, 5. Note that this always produces an answer if there exists an answer. This is because let's say the number 5 was lesser than or equal to required, but it still was not a part of the correct answer. Let's say some smaller numbers are part of the correct answer. So try to visualize how, if there exists a solution. Let's say that there existed a solution here which was 4 comma 3 comma 2 comma 1, but uh, if 5 is lesser than 10, we can change some of these entries here. So for example, we can remove 4 and 1 just to get 5, or we can remove 3 and 2 just to get 5. This is because, like, since we have all the numbers from 1 to n, instead of choosing a smaller value somewhere, if a larger value fits, we must choose it at that point. So because we also have smaller numbers, such that even this solution will give us a proper solution. Please try to visualize and think more about this. So the greedy strategy of choosing the largest possible element whenever possible works here. Note that it does not work for cases when we don't have the whole integer set. We don't have 1 to n. Let's say we don't have some numbers in between. At that time, we will have to use something like a knapsack or something else. But in this case, when all the numbers from 1 to n are present, you can employ this greedy strategy of taking the largest possible number whenever you can, because you always have smaller numbers and you have all the smaller numbers. You can have 1, 2, 3, you can have anything. And you also don't need to fit a size. You don't need a subset of size k. So if you just require 5 and you take 5 at the first try, then and there itself you get a complete subset. So let's look at my solution. It's just the implementation. So earlier, just to make the number smaller, I'm dividing x and y by their GCD. Now, as I said earlier, if n times n plus 1 times x divided by 2 times x plus y, it's not divisible, then the answer is impossible then and there itself. Otherwise, the answer is definitely possible. And I find a target value for ln now. And for the target value, I start with from the largest number. If it's greater than equal to target, I subtract it from target and add it to my subset. Finally, I just sort my subset because I wanted to compare with the answers. Then I print the size of my subset and I print the subset itself. I hope this is a fine solution for you. Thank you.
Hello everyone, I'm Tahir from Programming Club IIT Madras, and today I'll be explaining the solution to the third problem of Google Kickstart 2022 Round C. So basically in this question we are given n ants labeled from 1 to n, and we have an L centimeter long stick, and for each ant we're given its position pi for the ith ant and an integer di, which represents that initially is it moving towards the left or to the right. 0 if left and 1 if right. And we are given this rule that if two ants ever collide, that is, they are at the same position at the same time, they'll bounce off each other, and the ant that was moving towards the left will move towards the right, and the ant that was moving towards the right will move towards the left. So basically, what we're supposed to find is the sequence of indices in which the ants will fall off the table. So, like fall off the stick, and they'll fall off the stick if either their position becomes 0 or it becomes L. So basically here I've drawn an example. This point is 0 and this point is L. And here there are a bunch of random ants, and by R I've denoted if they are initially moving towards the right, and by L if they are initially moving towards the left. So like if we simulate this example, basically this ant will initially move towards the right, this ant will move towards the left, and then they'll collide, and then they'll kind of bounce back, and this ant will start moving towards the left, and this ant will start moving towards the right, and then this ant might fall off because it won't face any other ants in its direction. Similarly, this ant which was initially moving towards the left might bounce against this ant, and again they might switch directions, they might flip directions, and this ant will start moving towards the left, whereas this ant will change direction and start moving towards the right. And then this ant that was initially moving towards the right and this ant that was moving towards the left, they might collide somewhere in between, and they might change direction, and this ant will start going left and this will go right, and then this ant will fall off because it won't face any other ants in its way. And then this ant that was moving right and this ant that's now moving left, they might collide, and again they'll change directions, and this ant will fall off from the left as no other ant will be in its way, and this ant will fall off towards the right, as again there's no ant in its way. So here we see that these two ants will fall from the right part of the stick, and these three ants will fall from the left part of the stick. So, uh, so what can we observe here? So initially there were two ants that were moving right, and there were three ants that were moving left. And even finally, there are two ants that fall from the right of the stick and three ants that fall from the left of the stick. So, like one observation we can make, in fact, in general, is that uh, the number of ants that are initially moving left is equal to the number of ants that fall from the left part of the stick. And similarly for the ants moving towards the right, the number of ants that move towards the right, so I can just copy this, is equal to the number of ants that actually end up falling from the right half of the right part of the stick. So again, this can be easily seen because at every point in time, the number of ants that are moving towards the right and the number of ants that are moving towards the left will always remain constant. Because if some ant is moving towards the right and some other ant is moving towards the left and they ever collide, then their directions might, like I'll just draw it. So if one ant is moving towards the right and another ant towards the left, they would swap directions, and the ant that was initially moving right would move left and the ant that was initially moving left would move right, and hence the number of ants moving left and the number of ants moving right would remain conserved. They would just swap their directions, but the total would always remain constant. So at every point in time, the number of ants that are moving towards the right is always a constant, and the number of ants that are moving towards the left is always a constant. So this kind of proves this observation, that the number of ants that fall from the left part of the stick is equal to the number of ants that are initially moving left, and similarly for the number that fall from the right. So basically, that does it for the sequence of ants that fall from the right and the sequence of ants that fall from the left. Because we know that if two ants were to fall from the right, it can only be the rightmost two ants. No other ant from the left three could ever fall from the right part of the stick, because if they were to fall, then they would have possibly uh, collided with some other ant and flipped its direction. So if we know the total number of ants that fall from the right part of the stick, then we know that those must be the rightmost ants. If say k number of ants fall from the right part of the stick, then we know that that must be the rightmost k ants, and the remaining n minus k ants which would fall from the left part of the stick, because initially there were k ants that were moving right and n minus k ants that were moving left. So that does it. So from that we can basically get the sequence of ants that fall from the right and the sequence of ants that fall from the left. But what about the order, basically the time at which they fall off? So for that we can make another very useful observation, that um, okay, so assume for a few minutes that say every ant were identical. There were no distinction. They didn't have any indexing on them. They didn't have any like number printed on them. So say like for example, take this example right here. This ant must have collided with this ant somewhere in between, or I'll just redraw it for clarity. Say there was some ant here, some ant here. This ant started moving right and this ant started moving left, and at the midpoint of their paths they collide and they swap directions. Now basically, if let's assume that they did not have some label on them, all the ants were identical, then this situation would basically be exactly identical to saying that these two ants in which the left one was initially moving right and the right one was initially moving left, say they just passed each other without actually colliding or swapping their direction. They just passed each other and this ant kept moving left, this ant kept moving right. That would essentially be identical to this scenario where they swap directions, because it's basically like after they collide, the right ant would start moving left, but in the second scenario, the ant that was initially moving left will continue moving left. So it's like they kind of exchanged labels in a way. So as for the time when they would fall, these two situations are perfectly identical. Saying this ant will collide and then go left and fall off from here, and this ant collides and goes right and then falls off from here, is essentially the same as this ant just going straight and falling off, and this ant just going straight to the left and falling off. The basically the times at which an ant would fall from the left and the time at which some ant would fall from the right would be the same in both scenarios, even though the ant would be different. But again, if the ants were identical, this wouldn't really matter. So like why is assuming that they are identical here useful? Basically because in this case, we have already decided the sequence in which the right ants will fall off from the right ants and the sequence in which the left ants will fall off the left part of the stick. So what really matters, so we can basically find out the time by like as follows. For every ant that's initially moving right, what we can do is we can take the total distance, its total distance from the right end of the stick, and that will be the time in which that ant would fall from the right part of the stick, given that it doesn't collide with any ant, it just keeps moving straight along its path. Now if we introduce collisions, again this would essentially be the same, because every time it collides, some ant kind of takes its place and continues going right, and if that ant collides with some other ant, the third ant would kind of continue its traversal to the right and until it reaches the right end of the stick. So as for the times at which ants would fall off the right part of the stick, it's sufficient to just check for every ant that's initially moving right and find its total distance from the right end of the stick, and that would be the time in which some ant, not necessarily that ant, some ant would fall from the right part of the stick. Similarly, for ants initially moving left, we can calculate that distance from the left end of the stick, and that would be the time at which some ant, again not necessarily that ant, would fall from the left end of the stick. So this works for all of the ants that are initially moving left. So we have, so for this problem, we have these crucial observations that first of all, if initially say A ants were moving left and B ants were moving right, then at the end, the leftmost A ants will fall off from the left end and the rightmost B ants will fall off from the right end. It's not required that the leftmost A ants all initially start moving left, but we know that the leftmost A ants will end up falling from the left end. So that is the number of ants that are initially moving left is equal to the number of ants that fall from the left part of the stick. And then our second, this was for the sequence of ants that fall from the left and right part. And our second observation, our next observation was to calculate the times at which they fall. For every ant that starts left, we calculate its distance from the left end, and that is the time at which some ant will fall from the left end. And for every ant that's initially moving right, we calculate its distance from the right end, and that will be the time at which some ant falls from the right end. And as for the sequence at which they fall, the rightmost ant, the initially the rightmost ant that's the rightmost ant would be the first ant to fall from the right end, right? I mean, like obviously. So we, out of all these distances we have calculated for all ants that are initially moving right, the minimum distance, the minimum time will correspond to the rightmost ant. Similarly, for all the ants that are initially moving right and for the corresponding times we've calculated at which some ant will fall from the right end, the second least time would correspond to the second ant from the right end falling from the right end of the stick. So basically, say we maintain in a list L and a list R the sequence of times at which ants fall off from the left end and the sequence of times at which ants fall off at the right end. The minimum entry here will correspond to the leftmost ant falling from the left end. The second minimum entry here would correspond to the second leftmost ant falling from the left end. And similarly in a right list, the minimum entry will correspond to the rightmost ant here falling from the right end. And the second minimum entry will correspond to the second rightmost ant here falling from the right end, and so on. So in this way, we can also calculate the sequence in which the ants fall off by calculating the times at which the ants fall off, by kind of mapping these times to ants from their distance from the left end and right end. So basically, as for the code, what I initially do was, of course, I scan the total number of ants and I scan the total length of the stick, and then I maintain in the array D the uh, the initial direction in which the ith ant is moving, and I made an array of pairs P in which I'll store the position of the ant and the index of the ant, because later on I'll sort this array and the indices might get a bit mixed up. So then I initialize two variables a and b to 0. A will basically store the total number of ants that are initially moving left, which will also be equal to the total number of ants that fall from the left end towards the end. And similarly in B, I store a total of number of ants that are initially moving right, which will later be equal to the total number of ants that fall from the right end. And I've maintained two vectors VL and VR, in which I'll store the sequence of times at which ants will fall from the left end and ants will fall from the right end, respectively. So then in this for loop, I scan first the first entry of the pair, which will correspond to the position of the ith ant, and I do pi dot second is equal to I, because that will store the index of that ant, and we have to print the sequence of indices. So that's why I've stored the index as well in the pair. So then what I do is, if di is equal to 0, which means the ith ant is moving left initially, I do a plus plus, and I push back in the vector VL pi dot first. Pi dot first is its position, which is also its total distance from the left end of the stick. Or else, if di is not 0 and di is 1, I do b plus plus and I do vr dot pushback l minus pi dot first. So here l minus pi dot first will be the distance of that ant from the right end of the stick. So here I've calculated the sequence of distances, which is also the sequence of times, since the speed is 1 centimeter per second, and similarly here. So then I'll explain this part of the code in a little while. So then what I do is I sort this array so that I can get all the ants in order of their positions from the left end, and I sort both the vectors VL and VR so that I can have both of them in the sequence of times in which ants fall off the stick. So VL, after sorting, VL will store the sequence of times in ascending order where ants will fall from the left end of the stick, and VR will store the sequence of times in increasing order where ants will fall from the right half of the stick. So now I've maintained like some pointers. I initialize L to 0, R to n minus 1, and I have like a kind of a pointer, a multi-dimensional pointer, which I initialize to 0, comma 0. And then I do for I from 0 to n minus 1 if VL of PTR0 is less than VR of PTR1. That is, if the first ant that falls from the left end falls at a lesser time than the rightmost ant that falls from the right end, then what I'll do is I'll print the index corresponding to that ant which fell from the left end, because this means that the ant that first fell from the left end falls before the ant that falls from the right end. So then I print the index corresponding to the left ant. I do L plus plus and I do PTR 0 plus plus. Or else, if VL of PTR 0 is greater than VR of PTR 1, that is the ant currently falling from the right end falls before the ant that's going to fall from the left end. Then I print pr.second plus 1, that's the index corresponding to the ant that's currently falling from the right end. And I do r minus minus ptr1 plus plus. Here ptr0 and ptr1 basically corresponds to that currently which in the array corresponding to, like, VL stores the order of times of ants that fall from the left end. So out of all those ants, which number ant am I currently talking about? And similarly, PTR1 corresponds to, out of all the ants that are going to fall from the right end, from the rightmost ant in that order, which ant am I currently kind of talking about? So initially I compare VL0 with VR0, and if say VL0 is less than VR0, then that means the first ant has fallen off. And now I'll do PTR0 plus plus, so that now I can talk about the second ant that falls from the left end and compare that with the first ant that falls from the right end. And my LNR is basically stores the positions of the ants from the left and right end. Like the leftmost ant, L corresponds to the leftmost ant and R corresponds to the rightmost ant. And once say the leftmost ant has fallen off, I do L plus plus, as in the next ant that might fall from the left end will be the second ant. And similarly R minus minus if the current if the current right ant falls quicker than the current left ant. Or else if VL of PTR0 and VR of PTR1 happen to be equal, then what I do is I compare the indices of these two ants, because the question has specified that if two ants fall at exactly the same time off the stick, then we should print them in the order of, in increasing order of the indices. So I do PL if basically if VL PTR0 is equal to VR of PTR1, then I check if PL dot second is less than PR dot second. If it is, then I print the index corresponding to the left hand, and again I do L plus plus PTR0 plus plus, or else I print the index corresponding to the right hand and I do R minus minus PTR1 plus plus. So this will basically print the indices of the ants in the order in which they fall off the stick. This whole part kind of takes care of checking that whether the next ant is going to, like, comparing whether the next ant is going to fall from the left part and the next ant is going to fall from the right part, which one falls first. And the reason here I've just pushed infinity into both VL and VR is because once I have exhausted the vector, basically once I've exhausted all ants that are going to fall off from the right end, say there are A ants that fall from the left end and B ants that fall from the right end. Once I've taken care of all those B ants, I'm still going to compare VL-PTR0 with VR-PTR1. So I basically want to set VR of PTR1 to be something really large, so that VL of PTR0 will always be smaller, and I can always say that the next ant that's going to fall off will be from the left half and not the right half. So this is essentially kind of similar to putting some imaginary ants here. Like there are two, in this example there were two ants that fell from the right half and three that fell from the left half. So I put two imaginary ants here. This ant will fall from the left half at infinite time, and this ant will fall from the right half at infinite time, basically. So that's why I did this, so that these comparisons will make sense. And setting this to infinity, this will always be smaller, or setting this to infinity, this will always be smaller. So yeah, like that about does it. So this will print the order of indices of the ants in the order they fall off, and if any two ants ever fall at the same time, it will print their indices in ascending order. So that's basically the solution to the C part of uh, the Kickstart round.
Hello guys, I'm Aditya C, username ADCAB2. Let's now look at Google Kickstart Round C's last problem, palindromic deletions. So the essence of the problem is this: you are given a string of length n. You have to perform the following process n times. Pick an index in the current string uniformly at random. Delete the character that index. You'll now get a string with one lesser character. If the new string that you get is a palindrome, you eat a piece of candy. And now you're asked what is the expected number of candies you will eat during the game. So if you check through all possible ways in which you can, pick indices from the string and delete characters, you'll eat some number of candies. Now divide this by the number of ways in which you can, pick indices in the string and make it smaller and smaller, and that will be the expected number of candies. So if we see the constraints, the first one has n going from 2 to 8 and the second one has n going from 2 to 400. So to pass test set 1, we can come up with a brute force way of solving the problem. So let's try to understand the question with the example given in the question. So one of the examples given is ABA. I have written that example in this diagrammatic way. So now if we see ABA, we can uniformly make it into BA or AA or AB with equal probability, which in turn will become A or B, A or A, B or A, and all of which will become a null string. So I've underlined all the palindromic strings that we get in red in color. So if we see the expected number of candies you'll eat is, so this is one possible path. So this is the one circled in black is one possible way in which you can divide the string. So each of these single letters corresponds to one way of dividing the string, and the way we can get by drawing a path from this source string to this single letter alphabet, or to the null string as well. So the number of ways, or the expected number of candies will be, we'll eat 6 plus 6 plus 2. This has to be counted twice because it occurs in two parts. So 6 plus 6 plus 2 divided by the total number of ways in which you can do it will be 6. So it will be 7 by 3. And we have been asked to use some modular arithmetic. So we are supposed to do modular division. So if the fraction is p by q, then we should output a number e such that e into q is congruent to p mod 1e9 plus 7. So we basically know that this will be p into mod inverse of q, where mod inverse can be calculated using Fermat's theorem. It's something you can Google up as well. So essentially we'll just have to find the numerator, find the denominator, compute the modular inverse of the denominator, and multiply the numerator, take mod, and that will be the answer. So to solve the test set 1, we can try a brute force approach. So basically just follow this itself, like take a string, delete one character arbitrarily, you'll get these strings, and do the same thing for these strings. So it will be a recursive approach. So let's look at the recursive approach that we have. So given a string, we get an input from the string and we initialize answer to 0, and we do the processing in a function called func, right? So this func takes a string as input. What it does is it deletes one character of the string at random. So we first delete the first character, then the second character, third character, and so on. So we'll get all of these cases. So in each of these cases, we'll check if this word is a palindrome or not. So for that, we again have a function ispal to check if a string is a palindrome or not. And if the string obtained by deleting one character is a palindrome, so basically t dot erase of I comma 1 will erase one character at the ith position. If it is a palindrome, then we'll have to increase the answer by some amount. We'll see why it is this. And after increasing the answer, we'll have to process this string, right? So that's what we're doing. We are given this string, we are forming these set of strings, and we are processing each of these strings independently. Now, if one of these strings is a palindrome, then how much should I increment the answer? So our whole idea is to brute force. So we want to find the number of ways in which we will get this string. So what will be the number of ways? So our whole idea is to brute force. So we want to check the number of ways we will get this AA when we know we delete a character arbitrarily, and that will be given by the number of paths that we can have from going from AA to this. Because from AA, by deleting the first character, we'll get this A, or we can delete the second character and get this A. And in both of these ways, we will come at AA, and AA is a palindrome. So we'll have to count AA 2 times. Suppose say we had AAAA, right? In that case, we'll have 4 cases, AAA, 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 and in each of these 4 cases, we'll again split. So this AAAA must be counted 4 factorial times, because this string can be made into the null string in 4 factorial ways, right? Now, how is that? Because in the first step, we have 4 choices to delete any of these 4 A's. The next step, we'll have 3 choices. We can delete any of the 3 A's, first, second, or third, and so on. So we have 4 into 3 into 2 into 1 ways, 4 factorial ways. So this string will get counted 4 factorial times because there are 4 factorial paths starting from here and ending at a null string, right? So answer plus will be equal to factorial of the size of the string. So SCFT, I have defined it using a hash defined such that it will give me the size of the string. So if a string is a palindrome, I'll have to count it t factorial times, where t is the length of the string, right? So here t is a string itself. So answer plus equal to factorial of length of t. And now if I do this over all possibilities, so like for each possibility I'm deleting a character and processing it, and I'm doing this for all characters in the initial string. So this will kind of brute force through all paths. Like I'll start from here, go here, here, here. For this I will again expand the whole way, then for this I'll expand the whole way, then for this I'll expand the whole way. So I will essentially go through all strings in this tree kind of structure, and that will be the recursive function that I've written. And I'm declaring a global variable answer. I'm initializing it to 0 here, and after doing func of s, answer will get incremented appropriately such that the final answer will have the total number of palindromes that I will encounter if I do all possible n factorial ways of processing the string as they've told, like delete a character and then process the string again. So there are n factorial ways of doing that, and I'm computing the number of candies I will eat if I do all such n factorial ways of processing the string as they've told. And now as they've asked for the expected value, I'll have to divide it, I have to multiply it with mod inverse of denominator. So denominator will be n factorial because that is the number of ways in which you can do the processing. So denominator will be factorial of SG of s, and then I'll have to multiply my answer with mod inverse of denominator and take modulo again and output the answer. And that will be how you will solve the easy test case. So that is a brute force way. It will kind of take around n factorial function calls, and that's not going to work for n equal to 400. So in such questions where you had a brute force idea and there's not much logic in which you can condense the question into smaller parts, the best thing to do is dynamic programming. So if I am going to do dynamic programming, then what can I do? So we have a string, right? We have a string that is given to us, and now what is the sub problem that I can choose to solve? So one interesting sub problem that we can see is maybe dp of I of j, where dp of I of j will give us the number of palindromic subsequences in s of I to j, right? So this is something that feels intuitive, some general dp problems that we solve, right? So dp of I of j will be the number of palindromic subsequences in s of I to s of j. Why am I focusing on palindromic subsequences? Because what this process does, it deletes characters arbitrarily at different positions, and the resulting string will be a subsequence of the original string. So if the subsequence is a palindrome, we are eating a candy. So it makes sense for us to count the number of subsequences in one part of the string, right? Now, does this work, or is there some issue with this? So let's say we have ABABA, right? So one possible subsequence is AAA, which is palindromic, right? That I'll get by choosing this, and this character. Now, say I want to calculate, like the previous method, I want to calculate in all the n factorial ways. If I sum up all the n factorial ways of processing the string, how many candies will I eat? Say that is what I want to calculate. In that case, I have two things. First, the number of ways in which you can get to the string, and the number of ways in which I can get from this string to the null string, right? So these two numbers matter to me because I'll have to multiply these two numbers, and that will be the number of times this string will occur in my processing, and that will be the number of candies I eat on seeing this string, right? So now what is this number? Going from this string to this string, I have to delete, let's say this has length n, this has length k, and null string has length 0. So I have to go from a string of length n to a string of length k, and the k characters that I'm choosing are fixed, right? Because I want a, say in this order. Say it is the indices that matter. So let's say I'm focused on the indices and not the characters themselves. So I want the substring 1, 3, 5, and in one move I can delete one character from the string, right? So what are the number of ways to go from this to this? So I have to delete 2 and 4, and I can delete them in any order. So basically, to go from n letters to k letters, I'll have n minus k letters and I can delete them in any order. So it'll give me n minus k factorial base of deleting letters. And now going from here to null string and doing deletions, that will take me k factorial base. So say I find one substring 135, then the number of times that will come in my approach will be n minus k factorial times k factorial, right? And now note that this depends on k, which is the length of the string, and it doesn't depend on the alphabets in the string exactly. Like for all I know, this could have been ACA as well. It only depends on what indices these are, 135. So it just depends on the length of the substring, right? But it depends on the length of the substring. So just finding dp of I of j is not going to help us. We'll have to find dp of ijk, where dp of I of j of k will denote the number of palindromic subsequences of length k present in the substring s of I to j. Because for each length palindromic subsequence, I have a different multiplier that I have to multiply, right? So I can just find the number of palindromic subsequences in the string, and for each, say for a k length palindromic subsequence, multiply n minus k into k factorial, and adding all of those will give me the number of palindromic subsequences present multiplied with the appropriate multiplying factor, which will give us the number of candies. So essentially I have two steps over here. So the first step, find dp of I of j of k, which is number of palindromic subsequences in s of I to j, right? And use dp, we get dp of 0 to n minus 1 of k, right? Now for each k length palindromic subsequence, you have to multiply dp of 0 n minus 1 k with k factorial times n minus k whole factorial, because each string will be encountered that many times in a brute force process. And now add values from 3, right? This is the kind of summarizes the approach that we have to do, right? So initially this is the dp state we're defining, then we have to do some dynamic programming to get this value, and then multiply this value with this and add over all k going from 0 to n minus 1, right? This is the approach that we have to do. So now we have found the optimal subsequence that we want to do dp for. Let's now try to find how we can get this, and for that we'll have to write a bigger subproblem in terms of smaller subproblems, right? For that, let's look at a substring, s from I to j, and let's focus on, say I want to find all palindromic subsequences of length k. So I want to find dp of ijk, and let us say I have computed this dp value for all substrings lesser than this length. So substring of I to j, let's say it has a length l. Let's say I've done this dp for all substrings having length less than l. So how can I find this? Now first I'll find this value which I would have already computed, dp of I j minus 1 k, and let's say I also find dp of I plus 1 j k. So in this method, if I find dp of I j minus 1 k, right, I'll just write that down, dp of I j minus 1 k. So that will include all palindromic subsequences that may or may not have the first character. And now if I do similarly dp of I plus 1 jk, that will include all subsequences that may or may not have the last character. But I am double counting this area, right? Because I'm double counting that area, I'll have to subtract it once. So minus, pardon my handwriting, it's the mouse, minus dp of I plus 1 j minus 1 k, since I'm counting that part twice, right? So I'm counting all palindromic subsequences that may or may not have the first character, adding with those that may or may not have the last character. Because I'm double counting the palindromic subsequences that might occur in the shaded region, I'm subtracting it once. Now, what is missing in this? If this character comes, it will get counted in this. If this character comes, it will get counted in this. But what if both characters come? So what if both characters are present in a palindromic substring? How will I count that? Now, for both characters to be present in my palindromic substring, these two characters must be equal because it's a palindrome, so the first and last characters must be equal. So now that we know the first and last characters are equal, so let us say the first and last characters are equal, I already found dp of I plus 1, j minus 1, k minus 2, right? So that will be the number of palindromic subsequences that have length k minus 2 and lie in this range. If I add these two characters to it, that will give me a palindromic subsequence of length k in this range, and that uses both the first and last characters. So if the first and last characters are equal, I'll have to add that as well to my question. So let's just look at the dp subproblem. So dp of ij val, so val is the k, we'll add dp of I plus 1j, add dp of I j minus 1, and subtract dp I plus 1 j minus 1, and adding mod is for modular arithmetic purposes. If the first and last characters of this substring are equal, then checking for domain, I'll have to add dp of I plus 1 j minus 1 val minus 2 as well, right? So this will give me the value of dp ij val. Now the base case initialization is that all substrings, all valid substrings of S will have one palindromic subsequence of length 0, that's a null palindromic subsequence, and all substrings of length L will have L palindromic subsequences of length 1 because each character is a palindromic subsequence of length 1. This is the base case, and now first I'll have to find this dp value for all. I have to go in increasing lengths because the assumption that we made was given a substring of length L, I have found the answer for all substrings having length less than L. So I have to iterate from length 2 to n, and I'm iterating through all possible starting points of my substring. Fixing starting point and length fixes the end point, and after fixing the end point, I am iterating through all possible subsequence lengths. So val equal to 2 to length. Now for each value, I am finding dp ij val using what we had discussed. Like first take cases where first character may be included, last character may be included, and some overlapping cases. And if both first and last character are included, that gets covered over here, and taking modulo for modular arithmetic purposes. So that will give us dp0 n minus 1, which will be the number of palindromic subsequences of length k present in the string. Now for each such palindromic subsequence, so going val equal to 0 to n, I'll have to multiply factorial n minus k into factorial k, multiply it to dp 0 n minus 1 val, and add that value to my answer, right? And doing this for all lengths from 0 to n minus 1 will give us the number of candies you'll eat if all n factorial crossing ways occur. And now again multiplying mod inverse of denominator, we will get the desired answer. And this is the solution to the hard version. So I'm declaring the dp array globally because they've set the constraints to be 400, and a 3D matrix 400 cross 400 cross 400, you cannot declare it within a function. That much space cannot be allotted there, so you have to declare it globally. So one mistake that people may make is not taking modulus over here, just taking modulus over here. So that is the mistake I had also done in the contest. So generally when you do modular arithmetic, try to take modulo wherever possible, right? Don't anticipate like we may not need to take it, just take it wherever you want to do. And that's the solution to problem D. If you have any doubts, you can just put it in the comment section as well. And if you like the video, do like, share, and subscribe. Thank you.